Thanks for coming. So I'm going to try to tell you about at least my perspective on the 2016 Nobel Prize in Physics. Most of the research that I'll talk about actually happened before I started doing physics. So I'll do my best to do it justice, and it'll be a bit from my perspective in terms of things that that touch on the research that I'm doing. So the Nobel Prize in Physics in 2016 was given to David Thouless, Duncan Haldane, and Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. Maybe a couple of things to note here. So first, actually, it turns out that half the prize was given to Thouless, a quarter to Haldane, and a quarter to Kosterlitz. That's not necessarily obvious if you just read the press releases. And of course, the Nobel process is a bit opaque, so we have to make our own interpretation of what's going on. My interpretation is that the and here divides the prize in this particular way. That in fact, it's in some sense acknowledging two contributions. The contributions from Thouless and Haldane to the understanding of topological phases of matter, and the contributions of Kosterlitz and Thouless to understanding topological phase transitions, which are slightly different things. Topological phase transitions describe, in this case, in this sense, describes the finite temperature phase transition, in particular the Kosterlitz-Thouless transition, or Berezinski-Kosterlitz-Thouless transition, in low dimensions due to proliferation of topological defects in the order parameter, which you can think of as unbinding of vortex-anti-vortex pairs. And so this idea that one could have a phase transition that's driven by topological defects is new and is recognized as part of this Nobel Prize. This kind of physics now appears in a variety of systems and is studied in superconductors, in superfluid helium, in Bose-Einstein condensates, all low-dimensional systems, two-dimensional systems or below. But it's this is important work. It's relevant to a lot of people that are working in our school, including Tapio and Chris. But it's actually not the subject of the talk that I'm going to give. So I'm actually going to focus on half of the. My apologies. I'm only going to focus on half of the Nobel Prize and talk instead about topological phases of matter. So what I'm going to talk about is phases of electronic matter that are not described by an order parameter. In this case, these phases are described by an order parameter, but rather by topological invariants. And so that's a second important aspect of physics, an important aspect of topology as it relates to physics that was recognized by this prize. And Thouless and Haldane, I think, were the major contributors to this understanding. Okay, so that's what I'm going to try to do today. Okay, so I'll start by describing a little bit of what we know about electronic matter. I'll try to start at a basic level. So a free electron, I'm going to draw lots and lots of dispersion relations, so energy as a function of wave vector or momentum. And we know the free electron has this energy, which is h bar squared k squared over 2m, so it's parabolic in momentum, or k. If we take that electron and put it in a periodic potential, then a few things happen. One is that there's this Bragg scattering when we reach the edge of the Brillouin zone, which opens up an energy gap. And the other thing that I've done here, maybe I should have said that first, is that I'm only describing this wave vector now using the block wave functions, which can be described with k vectors that are within this first Brillouin zone. So there's a couple of things that happen. I'm essentially folding all of the bands back into this first Brillouin zone, and then there's a gap that tends to open here. This already allows us to describe two different kinds of phases. Well, I guess I should say the reason this gap opens, you can think of this as, in some sense, there are two degenerate states here one which has a maximal overlap with the ions, and the other one which has minimal overlap, and there's a difference in energy between them. So this allows us already to describe kind of two states of electronic matter. One is if we consider, for instance, 1 electron per atom, that actually only half fills this band. So 2 electrons are needed, spin up and spin down, to fill the whole band. So if we have a half-filled band, this corresponds to a metal. And if we have 2 electrons per atom, we get an insulator. We get something that has a full band and then has some gap, energy gap for excitations. The difference between the metal and the insulator is that if we apply an electric field, we can adiabatically move these states to higher momenta here in the right-going states and lower momenta for the left-going states. And that creates some net current in the system. These have some group velocity to the right. These states have some group velocity to the left, so there's some current that flows. In this case, we have the full band, and nothing, applying an electric field doesn't do anything. It doesn't create any current. So this does not conduct electricity, and this does. And so that's the difference between a metal and an insulator. Okay, so that's basic solid-state physics. Now let's look at a slightly different system. Let's take this free electron in 2 dimensions, and we'll put it in a magnetic field. So classically, what happens to an electron in a strong magnetic field is that it would orbit in cyclotron orbits. The quantum mechanical version is not too hard to work out. We can just take this Schrödinger equation for the free electron, add in a vector potential, and in a few lines we can come up with a solution which we can map onto the harmonic oscillator. And so these solutions are harmonic oscillators. They're localized in space, and they have this ladder of energies that we're familiar with, where this frequency is the cyclotron frequency. So these energies are called Landau levels, and it says that these electrons now appear in discrete energies. And so our energy versus momentum relation is now totally modified. It has this hugely degenerate levels where all the electrons sit, and nothing between them. These levels are effectively localized. They have no group velocity, so they're not moving. And the question that one might immediately ask is that this system, this 2D electron system with filled Landau levels, is that an insulator? It certainly looks like an insulator. So if we take the Fermi energy and we put it between these Landau levels, then it's in a gap. We have filled, completely filled bands here, completely empty bands here. There's some gap to excitations. So it looks like something that should not conduct. But we can do the experiment. And this was done in the 1980s. It requires a very clean 2-dimensional electron system for various reasons. That this gap has to be well defined, and so that condition is that the mobility in the magnetic field times the magnetic field has to be large. So you need high magnetic fields and very clean systems. But if you do that, you measure something like this, and so. I'm plotting 2 things here. The resistance of the sample as a function of magnetic field starts out finite, and then it begins to oscillate as you create these Landau levels that are moving through the Fermi energy. And then at some point it actually starts going to 0 with these oscillations in between. And the Hall resistance actually grows, and then it has these funny plateaus where it's quantized over some large range of magnetic field. So importantly here, the resistance does not become infinite. In fact, it becomes 0, which is rather odd. So this system, even in this state where we have these well-defined Landau levels, conducts. It has a funny resistivity and conductivity tensor. So in fact, the diagonal resistivity is 0, reflected here, but the diagonal conductivity is also 0. So that looks like an insulator, but it's a funny insulator in that it has this off-diagonal conductivity, the Hall conductivity, which is quantized. That quantization is incredibly exact to about a part in a billion. And this quantum Hall effect, of course, resulted in the Nobel Prize in 1985. this is an insulating phase in the sense that it has this zero conductivity. It has a gap between to excitations, but somehow it differs from the insulator that I described before that was related to having a full band in the nearly free electron model. So to understand that, we can start to think about whether this is a phase transition, whether there's a different phase of matter. So phase transitions have been understood within the Landau picture of establishing an order parameter by spontaneous symmetry breaking. So, a magnet, for instance, breaks rotational symmetry by establishing a magnetization, particular magnetization direction, which is an order parameter and a broken symmetry. So that explains a number of phase transitions. So for instance, the liquid to solid or the magnetism, superconductivity within that framework. But in the case of the quantum Hall phases, there's no symmetry that's clearly broken. So, these phases where we have the quantized Hall resistance here or conductance, with this incredibly precise quantization where there's something clearly special about this phase, they don't macroscopically look any different than a phase with a different quantization or conventional insulator. So the answer comes from topology. Hopefully you've guessed that by now. So, what is topology? Something I don't really understand, but I can tell you that topology, everybody knows that topology says that a donut is different than a muffin, and a sphere is different from a coffee cup, right? Something like that, right? So, so the idea is that the sphere and the muffin and the plate are distinct somehow from the coffee cup and the donut because this one has a hole. So I can't continuously deform this structure into this structure without somehow breaking that surface. So, and then there's a mathematically rigorous way to tell the difference between a muffin and a donut. All we have to do is calculate the curvature, the Gaussian curvature of the surface of this object, and then integrate it over the entire surface of the object. So we do this integral, and we come up with a number. We can find this number g, and then the g is the genus, and it tells us which of these surfaces we have. And so if I do this integral over the donut, I get 1. And if I deform that donut into the coffee cup, it stays 1 the whole time, right? So it's a topological invariant. It's not sensitive to the details of the surface. I can, squeeze the surface a bit here and there, and it doesn't change. Okay, so it turns out that there's a topological invariant that's associated with the quantized Hall conductivity or the quantum Hall phase, and so this is Thouless's contribution. One of Thouless's contributions is to understand that this phase is distinct. These phases are distinct from each other and distinct from the conventional insulator by a topological quantity. It's a bit hard to describe that quantity, but suffice it to say that what is required is that I come up with a particular vector that is associated with every state in the filled band, and then if I do this integral, well, this is the contour integral, so this is the integral over the entire Brillouin zone of this so-called Berry curvature, then I will get an integer. The Brillouin zone actually is a torus because it's effectively each side meets the other side in a sort of a periodic boundary condition. So if I'm just integrating this particular quantity that's defined for every state in the Brillouin zone over the torus, and it gives me an integer, and it turns out that integer is the integer that describes the quantized Hall conductance. So this means that filled bands aren't all alike. They all have zero diagonal, longitudinal conductivity, but they can have different Hall conductivities depending on this topological property. So some of us may have studied quantum Hall effect before. You may have seen that in the quantum Hall effect, what's going on is that current flows along the edges of the sample. There's something funny that happens at the edges, and it's worth reviewing that, that there's another picture that sort of explains how this quantum Hall effect comes about. So I gave you this picture of Landau levels before, but any real sample is finite, and at the edges of the sample there must be some kind of confining potential which is keeping the electrons in the sample. And so that confining potential causes these Landau levels to bend up at the edges. And so if I put the Fermi energy somewhere here in the middle, it must cross the Landau levels at these edges. At these edges, there's these Landau levels actually become dispersive. So it turns out if you take that Hamiltonian we had before and you apply an electric field in it and a magnetic field, you'll find that there are 1D states that carry current in this E cross B direction. And these states are different for the different edges. They are dispersive, so they have an energy as a function of momentum. They have a group velocity, but that group velocity is actually along the edge. So these states carry current around the edges of the sample. You can think of them as these little skipping orbits of the electrons going around the edge. And notably, they only carry current in one direction around the edge. So that current can't backscatter. There's nowhere for it to go, so it actually flows without resistance around the edge of the sample. And then once you know that you have a 1D wire, the conductance of a one-dimensional wire is quantized, and so it's quantized in units of E squared over h times the number of 1D bands that are doing the conduction. And the number of 1D bands is actually the number of these Landau levels you have in the sample, so it's the same nu. And so the current is just nu E squared over h times the voltage that flows along the edge. And if you have this multi-terminal geometry, you can kind of convince yourself that in fact the longitudinal conductance will be the same because all of these contacts rise to the potential of the contact that you're using to source the current, and these contacts stay at zero potential because they're tied to this one that's at zero potential. And you can in fact work out this quantized Hall resistivity quite easily. So, and that's just from, it doesn't have anything to do with topology, it just has to do with knowing that there's an edge state in this system. So there's something that's actually quite deep that's going on here, that there's a correspondence between what's going on in the bulk and what's going on at the edge. And it turns out that that's actually guaranteed. So when gapless states always show up at the interface between topological phases with different topological indices. So in the quantum Hall effect, when we have an edge, we have an edge between this quantum Hall system, which has this TKNN number of 1, and then vacuum it's like a regular insulator. It has TKNN equals 0. And there's always going to be a state there that shows up at the edge, and it's always gapless and metallic. So this quantized Hall conductivity is a bulk property and it's an edge property. It's not that it's one or the other. A particle can be a wave. Quantized Hall conductivity is a bulk and an edge property. And in fact, if you do experiments only on the bulk, so if I take light and I shine it only into the bulk of the sample, then the electric field of that light will excite currents that are not parallel with the electric field. And so there's a Faraday rotation that's due to the Hall effect that's in the bulk of the sample, and it's quantized. And if I measure current by putting contacts on the sample, that current does indeed flow along the edges of the sample. And so both of these things are true. The Hall conductivity is quantized in the bulk, and it results in a current that flows on the edge. And they are necessarily two sides of the same coin. Okay, so that's kind of a fascinating thing about topological phases, is that whenever you have one of these things, as soon as you put two of them together, something new happens at the edge. All right. So the question then is that I described to you one system that has this TKNN number, which is not 0, and is so therefore topological. And the question is whether that's the only system. And so that's a bit more of a difficult question to answer. And the answer comes actually by looking at a curious place. I described band insulators before, where a gap opens up at the edge of the Brillouin zone. But it turns out that there are materials where this gap doesn't open up. And one of them is graphene. So graphene has bands that touch at this Brillouin zone boundary, and there's no gap, at least at a special point. And that's an interesting place to look, and that'll become clear in a minute. So graphene looks like this. It's this hexagonal lattice of carbon atoms. There are 2 atoms in the unit cell. They are identical, and it's the fact that those 2 carbon atoms are identical that prevents that gap opening. The band structure of graphene was worked out quite some time ago, 1947, within a tight binding picture. And it looks something like this. So it's quite simple to write down the band structure of just the pi orbitals of this graphene lattice. And what we see is a valence band and a conduction band. And they meet at these points. So those are the points where they're crossing, and that crossing does not get removed by a gap opening. So near those points, the dispersion is linear. So this is again, it's an energy versus momentum picture. So near those points, the dispersion is linear, and the Hamiltonian linearized in K or in momentum looks like this. This looks like essentially a Pauli spin matrix dotted into momentum, so a sigma dot p. So it kind of has part of a Dirac equation in it. So sometimes it's called massless Dirac particles in 2 dimensions, and no mass. But it has this funny form. And what the Hamiltonian here is a 2x2 matrix. It's operating on a wave function that's 2-component. Those 2 components are just the weight on the 2 atoms in the unit cell. So it looks like a spinner. And in fact, it turns out to have the properties of a spinner. So the wave function actually has this plane wave component, and it has this 2 vector, which is a spin. It's not the quantum mechanical spin of the electron, but it's a orbital effect of the 2 atoms having 2 atoms in a unit cell. But it has the properties of a spin 1/2. And that's generically true whenever you have bands that cross each other and there's a degeneracy that's not lifted, is that degeneracy is sort of generically protected by some kind of a spin. Okay. All right, so now we can try to answer this question. Are Landau levels the only system with this TKNN index that's non-zero? And the answer is no. There are other systems, and so the first such example is due to Haldane. So Haldane published a paper in 1988, a model for quantum Hall effect without Landau levels. And I can't even tell you what the second part means. Condensed matter realization of the parity anomaly. So maybe we can have another colloquium on the parity anomaly. And this is one of the figures from the paper, the first figure. And the model is what he calls 2D graphite. So that's what we now know as graphene. This is before we actually even had a name for graphene. The model is fairly simple. So it is this honeycomb lattice of a graphene-like lattice. But with a periodic magnetic field. So the net flux of the magnetic field is 0, and that allows for a periodic vector potential, which has the same period as the lattice. And that allows, it basically obeys the lattice symmetry, but it breaks the time reversal symmetry. So it could correspond to some kind of magnetic material. So it seems that it's at least possibly a realistic situation. And the idea is that without this magnetic field, we have the graphene Dirac cone, and then when you apply this periodic magnetic field, there's an opening of an energy gap. But it's and you have an insulator, but that insulator then has a quantized Hall conductivity. So there's no Landau levels here, but we do get this quantized Hall conductivity. So that's really interesting. This was kind of a curiosity for many years, of course, because graphene didn't exist and there wasn't any material that was known to have these properties. But then graphene did come along. We had to wait a while. So really the first experiments were done in 2003 or 2004. So Andrei Geim and Kostya Novoselov exfoliated graphite. using Scotch tape and little crystals, and rubbed it against a very flat surface, silicon dioxide on silicon, which really makes it visible in a microscope, and could make single layers of graphene. And we're able to isolate these single layers and put electrical contacts on them. And so these things really became available to study. And of course, again, that resulted in another Nobel Prize in 2010. So this got people thinking about graphene. It's interesting. Once something exists, many more people start to think about the implications of that. And so immediately some new implications were realized. So one is that people started thinking about what possible perturbations could be applied to graphene. This again is this sigma dot p Hamiltonian. So there's various things you can do. You can apply a sigma z term to this Hamiltonian, which tries to rotate this pseudospin out of plane. It corresponds to actually making these two atoms in the unit cell distinct. And that sort of, you can fairly easily realize opens a gap. But you could also you could also add in a spin-orbit coupling term, and that might correspond to when a spin-up electron scatters to a next nearest neighbor, it might have a higher probability of going to the left than to the right, and you'd have the opposite for spin-down. So that's something that that actually happens in solids. And it also opens an energy gap. But these two energy gaps are not the same. And they both have a gap in what you would call the bulk states, but if you look at the states in a finite width ribbon of graphene, you find out that the edge states look different in this case than in this case. And so this case has edge states that are crossing the gap. And so this is that's now typically called a topological insulator. So this actually happens without magnetic field. It's just due to spin-orbit coupling. And this is a two-dimensional version, and so often it's called the quantum spin Hall effect. And I'll try to tell you why. So this phase of graphene with this graphene with spin-orbit coupling has these edge states. It's insulating in the bulk, so in the bulk of a sample it's insulating, but there are these edge states drawn in red and green that just live on the edges of the sample, and they carry spin up. On this top edge they carry spin up to the right and spin down to the left, and on the bottom edge they carry spin up to the left and spin down to the right. So this whole system is time reversal symmetric. There's no time reversal symmetry breaking that's needed. It doesn't require a magnetic field. It's just due to spin-orbit coupling. And effectively, this is two copies of this Haldane model. The Haldane model used a magnetic field to produce this effect in all of the electrons, but spin-orbit coupling takes one spin-up electrons and has the Haldane model with a positive magnetic field and spin-down with a negative field, and gets the same thing, but no magnetic field required. The other thing that Kane and Millie showed is that this state is associated with an invariant, a topological invariant, and it's a Z2 invariant. So this TKNN number can be any integer. This invariant is either 0 or 1. And it says that there's really only two kinds of time reversal symmetric insulators in two dimensions in the whole world. They're the conventional insulators that we know about, like glass or wood or what have you. And then there are these, well, they're not 2D, so maybe that's a bad example. But and then there are these topological insulators that have these special edge states where the spins go in opposite directions. Okay, so that's kind of neat. So this actually became a reality. So it turned out it didn't happen in graphene. So graphene, the spin-orbit coupling is there, but it's really very, very weak. And so it's thought to be really the ground state of graphene, but it's just sort of, you have to go to really low temperatures to observe it. It hasn't happened. But in mercury telluride, the same effect should happen, but the spin-orbit coupling is much, much stronger, and so in fact this can be observed, and so this was observed in 2007. If you make a two-dimensional quantum well of mercury telluride sandwiched between cadmium telluride, you in fact get this band inversion due to spin-orbit coupling, and you get this state where you have just this current along the edges. And the signature, experimental signature of this state is that if you measure the conductivity from one end of a sample to the other, it's only carried by these one-dimensional edge modes. And again, each one of these modes has a conductance of E squared over H, and you've got essentially a spin-up mode on the top going to the right and a spin-down mode on the bottom going to the right. And so you get 2 E squared over H, and maybe it's hard to see here, but as they tune the Fermi energy into the middle of the gap, the conductivity just plateaus at 2 E squared over H. So normally it should be an insulator. You turn the Fermi energy into the gap. Well, so this is the insulating version, and the conductivity, this is on a log scale. The resistance is just going to infinity. It's to the level of measurement that they can measure. And here it stops at 2 E squared over H, saying that there's 2 modes, one on each edge of the sample, that are conducting. So there's other experiments that show that the current's flowing along the edge and that it's spin polarized, but this is the first experiment on this. Okay, so one of the really interesting things is that once we remove this need for a magnetic field, which has a particular direction, we're no longer required to have topological insulators that are two-dimensional. So once this idea was realized that we have this topological insulator in 2 dimensions due to spin-orbit coupling, this quantum spin-Hall effect, Kane and Malie and also Joel Moore and Leon Balance and Raj Roy, I think it's Raj Roy, realized all about the same time that there's a 3-dimensional version of this. The 2-dimensional version, again, and we have a 2D system which is insulating, but on the boundaries we have 1-dimensional edge states which are metallic, they conduct. So, and they have these opposite dispersions for opposite spins. So spin up would have a dispersion this direction, spin down this way on one edge, and then everything's reversed on the other edge. The 3-dimensional version then has a 3-dimensional bulk, which is insulating, and then 2-dimensional surfaces, which are conducting and metallic. And on every surface, there is there are conducting states where the direction of the conduction is also tied to the direction of spin. So typically the spin then is actually a sort of a helix that wraps around the Fermi energy, but everywhere the spin is perpendicular to the conduction direction. So these, that's not a proof that they exist, but it turns out that they do. Kane and Malie, Kane and Malie were actually able to show that these are described again by topological invariants. It turns out there are 4 of them. There's one really important one, which can either be 1 or 0, and it describes whether it's something called a strong topological insulator, which is the picture I just gave you, or if it's 0, you can have non-zeros in these 3, and you get something that's called a weak topological insulator, and it's basically a stack of these 2-dimensional topological insulators. But this is the one I think that is maybe the most interesting. This has this metallic state guaranteed on every surface. So you take this material and you cut it, you get a new metallic state on the surface, and it has this very interesting dispersion. Looks a lot like graphene on the surface. And so again, soon after that theory was done saying that these things should exist in principle, theorists actually came up with some materials where they could be realized. One of the important classes is this bismuth telluride, bismuth selenide class. And so these are calculations of the band structure of those materials. Maybe it's a bit difficult to see, but there are some bulk bands here. So this is a valence band and a conduction band, and there's a big gap between them. And then there are some lines dispersing through here. This is again energy versus momentum, and those correspond to the surface states, which cross and don't have a gap. And these were realized experimentally right about the same time. ARPS, angle resolved photoemission spectroscopy, is a nice technique which actually directly maps out the energy versus momentum, at least for states that are filled. And these are the surface states, and they do indeed have this crossing. And one can even find that the spin is polarized, and so these left and right moving surface states have different spin polarizations. And so everything, and now these materials have been studied by many groups around the world, and so it's very clear that these really are insulators, but different than conventional insulators. They're topological, and they have this metallic surface state. Okay. So lastly, so I think I've told you a little bit about how the concept of topological phases came about, and why, and there's a Nobel Prize, particularly for Thouless and Haldane in this context. So I'll tell you a little bit about my perspective on what use these topological insulators might have. So this has to do with the ARC Center of Excellence in Future Low Energy Electronics Technologies, which was just funded, which I am directing. This Center of Excellence is directed at a particular challenge, and that challenge is that we have an insatiable desire for computing. So the demand for computations is growing at something like 70% every year, the number of computational operations that's done on the planet. That has been largely offset due to gains in efficiency due to Moore's law. Not completely. So the energy that's used in computation is growing at maybe 7 or 8% a year, but much lower than the 70%. But we all know that Moore's law is coming to an end, and in fact, transistors are really ceasing in terms of gaining efficiency in energy per computation. And so the semiconductor industry realizes that there's a need to invent and reduce to practice a new information processing technology eventually to replace CMOS. So this comes from the semiconductor roadmap. And so the whole goal of the Fleet Center is to come up with a new switch that has vastly lower energy per computation. The approaches are rather specific. We want to look at new mechanisms for electronic conduction without dissipation at room temperature. So those might be topological edge modes that I talked about in this talk. Excitonic condensates, or non-equilibrium topological or superfluid states. And then the idea is to make sensitive switches based on either quantum phase transition, such as trivial to topological, or collective electron phenomena, such as a superfluid condensate. So I'll talk about just these two topological ones. So one of the themes of Fleet then is to come up with a topological transistor, and so that would be a 3-terminal device controlled by where the current from source to drain is controlled by a gate, and what that gate does is it can turn a channel material from conventional to topological, and so when this is a conventional insulator, it doesn't conduct. When it's topological, it would have these edge modes that carry current in one direction without dissipation. So there are a number of people in this team. There are 6 investigators at Monash. I think I can point them out. So there's myself, there's Mira, Chris, Nikhil, I found 4, Augustine, and Xiao Lang, who's here somewhere, right? So he's in the middle. Okay, so, and we have 3 different themes. So in addition to the topological dissipationless systems, we're looking at, again, excitonic condensates and dynamically controlled non-equilibrium systems. So I'll talk just a little bit about this because this is something that I'm doing research on, just to tell you where this is going. We talked about the difference between a conventional insulator and a topological insulator. the topological insulator comes about because of an inversion of the valence and conduction band. So there's typically an axis that one can run along. It could be concentration or strain or what have you, that will transform a regular insulator to a topological insulator. And what has to happen is the gap has to close in between. And so that can't be done because they're topologically distinct. It can't be done without somehow changing the topology, and that has to happen by going through a metallic phase. And so we know there's always a metallic phase in the middle. This is generically what's called a topological Dirac semimetal. So topological Dirac semimetals are at this quantum critical point between regular and topological insulators. And examples of that, again, are graphene, which has this touching of bands. And we know that we saw earlier that graphene can be turned into a topological insulator, for example, by adding spin-orbit coupling. So it turns out actually these things exist in 3 dimensions. And so this is something that was realized only fairly recently, that there are 3-dimensional topological Dirac semimetals. Sodium-3 bismuth is one of these. And so this has this Dirac cone, but in all 3 momentum directions instead of just 2 as in graphene. And there are other examples of these 3D topological Dirac semimetals. Cadmium-3 arsenic-2 is clearly one. Zirconium telluride may be one, and there may be others. So that's rather nice because if we have this topological Dirac semimetal, we can perturb it, push it one direction or another, and create either a topological insulator, which has dissipationless edge modes, or a conventional insulator, which is insulating. And there are examples of this, at least in theory. So for instance, if I take sodium-3 bismuth and I make it very thin, I can turn it into a conventional insulator just by confinement. And then if I apply an electric field, I can change that conventional insulator to topological, and it'll go through this semimetal phase in between. So this is the energy gap as a function of electric field, and it starts conventional, it goes down to 0, and then it becomes topological. And in this state, it would have this conducting edge mode that could be dissipationless. So this is exactly what we want. It's a topological transistor. It goes from insulator to something that has this conducting edge mode. And so this is a material that we're working on in the lab. So if you go over to New Horizons and look in the window, you'll see this machine here, which Mark, my postdoc who's here, calls the echidna. Because it has lots of spiny projections coming off of it. So this is a great machine. It allows us to grow materials like this sodium-3 bismuth and then transfer them into a scanning tunneling microscope at low temperature, where we can not only look at all the atoms in the material, but we can also do electrical experiments on that material. So these materials are actually grown on pre-existing electrodes on insulating substrates that are all wired up to do electrical measurements, and we can go in with the STM and image. These are sort of atomically flat terraces of this material, and these are the atoms with an STM. And I'll just show you a couple of results that have recently come out. So we've been able to make this material and measure its mobility for different samples with different carrier density. We get really nice mobility. This is about where people started with graphene at 6,000 centimeters squared per volt second and pretty low carrier density. This is a really fantastic sample that Mark and James have been able to grow that has really large terraces, and now they're mapping out the local Dirac point in this material with scanning tunneling spectroscopy. You can see this minimum, which corresponds to the Dirac point, and map out its spatial variation. And these are sort of maps of the spatial variation of the Dirac point. And the really nice thing is that we can get really close to the Dirac point in energy. So the Dirac point, it only varies by a few millivolts, 5 millivolts in space. And that's comparable actually to the very best graphene samples. So it tells you sort of how close you can really realize this Dirac-like band structure, how close you can get to the point of that cone. And it's comparable to the very best graphene samples. So that looks really good as well. So what we're trying to do is make these very thin films to see this transition to a conventional insulator, and then apply an electric field and see a transition to a topological insulator. But we're not there yet. Okay, so that tells you a little bit about the Nobel Prize, a little bit about what we're doing and how it relates to that, and hopefully that was educational. So I'm happy to take questions.
Thanks a lot. That was great. So, questions or comments? Everybody's hungry for scones?
How cold do these things have to be to work?
Well, that's an excellent question. So we really want to get things to work at room temperature, and people who are very observant will notice that the energy gaps here, this is something like 70 millivolts, and so it's bigger than room temperature, but it's probably not really big enough to prevent some leakage current at room temperature. So you probably need gaps up to 300, 400, 500 millivolts at room temperature to make a really good transistor that turns off. There are predictions for two-dimensional materials, topological materials that have band gaps in the bulk that are that big, and so we need to find those materials and grow them, and then find ways to make them into transistors. But we've got 7 years, so well, yeah.